So there are two things which you have to be. There are two things which we have to know. We have to learn about the trigonometric and exponential forms. These are two things that trigonometric or exponential forms, they allow taking powers and taking roots of complex numbers in an efficient way. And I have two examples now, which are exactly about that. One of them is about taking powers of complex numbers. The other one is taking roots of complex numbers. Now, powers with exponential forms, they're very easy because exponentials are very suitable for taking powers. For instance, the question 20 says find all powers of this number 1 plus I up to 10. So the first power, second one, third one, all the way up to 10. You can do it with the binomial expansion. You can. But exponentials here are very suitable, and that's the best strategy here to use the exponentials to find those. So if I convert this number to the exponential form, I did it once already, last week. Here's my express version of the conversion. The exponential form of this number is like this. You can see that from the graph of that number here. That's the vector which represents this number. Here's the x component, or real part is 1, and the imaginary part is 1. Obviously, angle here 45 degrees, or pi and 4. And the length of that number, by Pythagoras again, it's root 2. Now, if you go after the powers, you see the immediate answer is like this. You take your absolute value or modulus of your number to that power, and you multiply your argument with the same number j. So I use this letter j for my sequence of powers or exponents. Here's my j, and here's my j. And effectively, you can stop at this stage already because we just found the power. Just two lines, and this is it, but I'll take it a little bit further. First thing I'd like to observe that when you look at the powers in exponential forms, it gives you the geometrical transformation powers represent. I mean, when you take a complex number to a power, it will do something to this geometrical representation of the complex number, and this is something which is here. So when you make a step from the jth power to the jth plus 1 power, what happens? You increase this one by 1, you increase this one by 1. Given that this is the length of the representing vector, and given that this is the argument or the angle of the representing vector from the x direction, it means that geometrically this step from the jth power to j plus 1 power, you have to rotate your vector by 45 degrees, and you have to scale it by extra root 2. So if I want to picture all of these powers on my diagram here, I have to take this vector. Every next one will be a rotation of the previous one by 45 degrees, and it will be a little bit longer, like this. All 10 of them. The question 20, it asks for 10 powers. So this is my first z. This is the square, 45-degree turn, and a little bit longer. This number is bigger than 1, so we have the extensions. We have a stretching. It's the second power, another 45 degrees, another stretching. This is the third power, right? 1, 2, 3, 4. 1, 2, 3, fourth power. Sorry. This is the fourth power, another 45 degrees, another stretching. Fifth, sixth, seventh, eighth, ninth, and the last one they ask is the 10th. Is the one. You can, in principle, write for these numbers the algebraic form. You can, in principle, identify the... Or in fact, I mean, if you look at this graph, do I have any objections from the class? Yes, I abuse the scale significantly. I mean, because the stretch from this vector to this vector doesn't look like it's close to root 2, because root 2 is approximately 1.4 something. 1.4 is almost 40% extra. Doesn't look like this one is 40% longer than this one. That's true actually, because I wanted to fit everything onto this screen. I made the scaling actually small. If you want to see the actual scaling, see I put it only 10% rather than 40 something percent. If I want to make it the proper one, it will be rather strange. Well, it will be big picture. Look at this, what's going to happen. That's the proper scaling of the 10th power. You see, so it doesn't affect the actual process, but that's the proper scaling. So just to give you the perspective. Okay, let's just bring it back to original scaling because I want to just discuss with you the algebraic form of that. Now, you can in principle write the algebraic form for each of this number. It will be 10 numbers, or well, 10 numbers for the question, of course, but you can in principle write the algebraic forms for all of those numbers, the whole sequence of them, without restricting your j to between 1 and 10. And I think the skill of writing that, it's not a trivial skill because lots of numbers and you have to sort of exercise some systematic approach when you write them. So probably I will address this a little bit. If I were you, if I needed to write the algebraic form of that number, first I would look here and I realize that actually, because exponents, complex exponents, via Euler formula, they just cos and sine, we all know the periodic with the step 2 pi, with the period 2 pi, meaning that here I will observe periodicity when my j will step over 8, isn't it? Because 8 over 4, it's just exactly 2. So basically, if I want to write the algebraic form of those numbers, I want to present you some systematic approach to those algebraic forms, Cartesian forms, I have to make my presentation with the period of 8. So what I'm saying here is this. I have to look at the subsequences of my j of the type like this. All of them which are multiple of 8, all of them which are multiple of 8 plus 1, all of them which are multiple of 8 plus 2. There will be 8 different subgroups of my j indices. And for each of them, the result will be looking different. I'll give you all of these subgroups here. Here, all of them. 8k plus 3, 8k plus 4, 5, 6, and the last one is 7. Those of you who knows a little bit of the higher arithmetic, you know this is called the partial quotient. This is a remainder. So we split my sequence of integers into these subgroups according to the remainder these subgroups produce with respect if you divide them by 8 partially, by 8. Now, for each of these subgroup of indices, this number in exponential form can be written in algebraic form relatively compact. Look at this. For instance, if my j is 8k, look at this. Imagine here was, in position of j was 8 times k. Then the whole power here will be just 16. And this number will be 1, right? Because if you have 8 times k here, 8 over 4 is 2, 2 pi, it's just the full revolution, exponential is just 1. So for this value, if I want to write what the zj will be, if for this subgroup, if I would like to write what zj will be, the answer will be just 16 to the power k. This is the Cartesian form of these powers, not all of them, but only those which have multiple of 8 in the j group. This subgroup, and that's actually on my graph, it represents these numbers. The numbers will go along the x direction to the positive side. The subgroup which comes with the remainder 1, it's a subgroup here. It will be all of these powers. Again, if you imagine yourself putting this number in here, across this exponential form, what will happen here? This number, if you get rid of all of these 2 pi factors, will be just 45 degrees. And we know how to expand that into the algebraic form. This number will be like this. So that's the result. That's the algebraic form of this power for this subgroup of indices, or for this subgroup of powers or exponents. It's a lengthy process, but it's a systematic process which gives you the algebraic form, shorter version for the algebraic form of those powers in each of these individual subgroups. This one, again, imagine yourself putting this number in here, replacing j with 8k plus 2 in here. The result of this substitution will be this number. All of these numbers will be going up. 8k plus 3, these are the numbers which will go this way. Imagine yourself putting it in here. Well, 8k all the time will return 16 to the power k, and that's the number you will be looking at. (8k plus 4) is this one. And the result for that, again, if we put it, if you put this value across here, 8k here will give you 16 to the power k. 4 will give you extra 4. So the result will be like this. And negative will come from here. Because 8k here returns you 2 pi, factor of 2 pi. And 4 will give you just pi, which is in exponential form gives you negative 1. You have to do this. You have to, I mean, if you have any doubts what's happening on the screen right now, you have to put this number, literally take the number, sub it in, and see and finish the arithmetic. I'm jumping some steps here, but I don't think if I presented all of these details here, it will make any good to you. It will be much more good if you do it with your own hand, or if you can't do it from the top of your head, like right now. Well, the remaining of these groups will be the value. This value, as the numbers sitting here, is the values you will come up with if you take this across here. And the last two, well, 6, the remainder 6 is the group of powers which go down, is the value. When it goes across here, 8k here will give you 16 to the power k, 6 will give you 8, and negative 1 will come from here again. Actually, it's my omission, this I is missing here, I'm sorry, it's a typo, of course. Because I said it go down, it should be the imaginary number, so the I was missing here. And the last one is again the bisectorial direction. This is now in the 4th quadrant, and that's the value for that. So if you ever embark on this long quest of presenting the Cartesian form for the numbers, that's what you have to do. So you had something? Go ahead. Oh, yeah, of course I'm missing. Thank you. Thanks. It's typo. Thanks for reading that. Okie dokie. Well, you can develop this even further. Do you see the development? I mean, this structure I presented to you, you can shorten it a little bit, make it still keeping the structure, but shortening this a little bit. We can do, rather than group of 8, I mean, rather than groups of remainders by 8, we can do remainders by 4. Because you see, these two opposite to each other, they will be just altering by minus sign. So rather than writing 8 groups, and I'm not saying you can do it like I mean, if you experience with that, probably you can do it straight away from the top of your head, straight away go to the groups of 4. But in general, you still have to do the 8 first before you present the condensed version. Look at this. I can combine the groups of powers going this way with the groups of powers going this way, and the group of powers going this way with the group of powers going this way, and all of them, which go in the opposite direction, I can combine them together. Look at this. Here's the combination. This one will be grouped with this one. So this time, I'll take the groups of the indices like this. Remainder after the division by 4 rather than 8. Because if I do that, this group will have these indices together with these indices. And that will be 2 directions, one of them this bisectorial and the other one which goes in the opposite way, which is hidden right now. And if I take this, if I combine these 2 together now, the result here which you can put will be like this, negative 4 to the power m. This subgroup within this group, it's the one where m is equal double k. If you put here double k, you will come up with this result. And this subgroup within this group, it's the when m equal double k plus 1. If you put here double k plus 1, you will come up with this result. This group will combine this and this, remainder 1 and remainder 5 with respect to 8. It's a good exercise, especially if you're not so good with the numerical arithmetic. It's very good exercise. And that if I combine these 2 groups, this group of values and this group of values, the result here, or you can do it directly, in fact, you can take this index and you put here across the exponential form. It's the other way to do that. You can take this group and put it across here. The result of that will be this combination. And the other 2 is like this. So two things you can learn from here. Oh, you can learn lots of things from here, but two which I can say, well, which come to my head straight away. Taking the number to the powers, an exponential form is very easy. But converting back to the algebraic form, not so easy. It doesn't mean if you do it the other way, it doesn't mean if you do it via binomial formula, it will be easier. No, it won't be. You will still hit the same splitting in different subgroups. But this conversion, it requires the knowledge of the geometrical structure of the powers and knowing of the numerical arithmetic a little bit, the remainders and stuff like this.